Okay, color magnitude and color diagrams in the optical. So in the past, I have dealt with quite a bit of anxiety from night-type teams who just get themselves all spun up because they have a lot of anxiety trying to understand color magnitude diagrams. Well, let me try to put some of that anxiety to rest, because it turns out you already know what color magnitude diagrams are, even if you don't know them by that name. Your astronomy textbook almost certainly has a diagram something like this HR diagram or Hertzsprung-Russell diagram, at least in this cartoon kind of fashion, right? Where it's got luminosity on the y-axis and spectral class or maybe temperature on the x-axis. So usually it's plotted with hot on the left and cold on the right. So spectral class, OBA, FGKM on the x-axis. But if you do that as temperature, the numbers are increasing to the left, decreasing to the right. Sometimes that makes people have a headache, but this makes physical sense for reasons I will explain shortly. Okay, so this is hot temperatures to cold temperature. And then we've got bright things at the top and faint things at the bottom. So this is, look, it's in the log, 10 to the 6th, down to 10 to the minus 4. It's in the log, but look, this is absolute magnitude. So we've got small numbers at the top and large numbers at the bottom. So the strict mathematicians around you are going to have a really bad headache, because we've got small numbers at the top and big numbers at the bottom, and small numbers on the right and big numbers on the left. Well, that's because at the end of the day, this is a color magnitude diagram, and we want bright objects at the top, hot objects on the left. Okay, so remember, we got bright objects and faint objects, blue objects and red objects. So technically, an HR diagram is in theoretical space because it's luminosity and effective temperature. But what we're measuring is brightness and color. So when we place things on this diagram, it is really a color magnitude diagram. So you already know something about color magnitude diagrams. Things in certain regions of the diagram are understood to be certain kinds of stars. So if I told you, if I give you a new object and said it's here, what is it? It's a giant, right? If I gave you a new object here and asked you what it was, what is it? It's a white dwarf, right? So you already know something about this diagram. You already know that if I tell you where something is in this diagram, you can tell me something about it. So things in certain regions of the diagram are now understood to be certain kinds of stars. And so if you plop a new object in one of those locations, you can make a guess as to what it might be. So this is a stylized, cartoony HR diagram. Reality is a little messier. This one is a little bit closer to reality. This is all real data. These are Hipparcos stars. So Hipparcos was a European mission from the 90s that was measuring distances to stars. So given the true distances to the stars, we can plot absolute V magnitude here. So we don't have to plot observed. We can correct for distance and plot absolute magnitude. And then we've got color, B minus V here. Remember that B minus V is straddling the peak of the effective temperature, the peak of the black body function. So we can map B minus V to temperature, and this can be mapped to luminosity because it's absolute magnitude. So now you've got that same kind of shape that we saw in the cartoon earlier. We've got the giants over here, but you see that it's got scatter because it's real data. Any random patch of sky you pick is going to have stars at different distances. So if you don't have distances to the stars, it's going to smear out the main sequence here. And you're going to end up with some galaxies floating around in there too. Now that we've got young stars to worry about, as most of my night-type teams do, you have an additional complication because the young stars are all going to be above the main sequence. So here is luminosity and effective temperature. Again, it's a cartoon fashion. So we've got the main sequence here is just a line with no bumps or wiggles. And we've got some evolutionary tracks. So a 15 solar mass star on its way to the main sequence, because remember the main sequence is where it's burning hydrogen. So a 15 solar mass star, before it starts burning hydrogen, is going to appear in this diagram pretty red, but it's going to move pretty rapidly blue until it ignites hydrogen. 9 solar mass is going to do that too, but a little bit slower. Same for 5 solar mass. By about 3 solar masses, you get some different bumps and wiggles. You get things that move predominantly down. Something like our sun is going to move down for a while and then left before igniting hydrogen. Something lower mass is going to move basically vertically in this diagram. So again, this is a cartoon version. These are isochrones, so they're lines of constant age isochrones. So something that is near that line is 10 to the 4 years, 10 to the 5 years, 10 to the 6 years, 10 to the 7 years. Okay, so this is actual data. This is actual models, rather, not actual data. These are actual models. So again, luminosity and temperature, both in the log. The blue lines are lines of constant mass. The blue numbers are the masses in solar masses. The red lines are isochrones, or lines of constant age, with the ages given as shown. These are models. They're not empirical data, and they're not analytical equations. They're models. They're people who created model stars in computers and ran them over time with different compositions and masses to try to figure this out. Hayashi tracks are the ones that are more or less vertical. They're contracting onto the main sequence while they're fully convective. The Henye tracks are the ones that are kind of horizontal. They're the ones that are that are moving horizontally because a radiative core is formed. Okay. This is what everyday reality looks like in its messier. So this is several fields in Orion, actually, out of part of my thesis. So this is not corrected for distance. This is observed I band versus V minus I. It's not quite V versus B minus V, but in this context, it's similar enough. And you can see by eye that there's this concentration here, and then there's a gap, and then there's this. Okay, this concentration is the group of stars that are likely members of Orion, because in Orion we've got a dark cloud blocking out most of the background. This is mostly foreground stuff, and that's stars in Orion. This is another view of the same fields. This is I versus V minus I. This is the zero age main sequence. In other words, stars in Orion at that distance should be on this main sequence, but you can see they're not. You can see they're well above the main sequence. This dashed line is a line that we drew through that gap to distinguish the field stars from the stars we took to be part of Orion. And you can see the spectral types across the top corresponding to the colors in V minus I. So remember that magnitudes include an implicit distance, but colors do not. So color diagrams, not color magnitude, but color diagrams can help in identifying sources. It is somewhat rarer to find optical color diagrams. Usually optical diagrams are color magnitude, but you do see color diagrams. This is UV excess. So again, it's from my thesis. I plotted U minus V increasing going down. I'm not the only one to do this, but now I hate it. So I'm going to flip it around. So this is U minus V increasing going up. I'm going to go back so we can read the characters. V minus I is increasing to the right. And then I've got spectral types across the top indicating how it corresponds to the color. So I'm going to flip it around. Let me flip the axes so you can read them. Okay. This solid line is where the main sequence is. In other words, this is where stars without dust who are just newly igniting hydrogen should be. And you can see that I've got a clump of stars hovering around that line, which is good. The reddening vector, remember reddening? Reddening is going to push it up and to the right, because it's going to push it redder in U minus V, which is up, and redder in V minus I, which is to the right. So it's going to push it up and to the right. So all of these stars that are hanging around here are reddened main sequence stars. In other words, they should be hovering around the line, but they've been pushed up and to the right because of the dust between us and them. All of these guys down here are ones that shouldn't be there, right? Because they should be hanging around the main sequence relationship, or they should be over here because of reddening, but they're not. They're down here. These are distinctly different than the neighbors. These are ones that have more UV than you expect. These are the UV excess stars. And the reason they have UV excess is because they're actively accreting gas and dust from their disk. So there you go. This one is an IFAS color diagram. So this is R minus H alpha versus R minus I. So R and I are broadband colors. H alpha is a narrowband color. So again, reddening is going to push you up and to the right. So it's going to make you redder in R minus I this way and redder in R minus I this way. So this is the reddening vector here. The green line is where the inactive main sequence stars fall. These are all the stars in the field for a different NITARP team from AFGL 490. This stuff here, these guys here, so the giants, the ones that are after the main sequence, kind of live around here. But this smear right here, you can see it's parallel to the reddening vector. This smear right here is reddened background giants. This smear right here is main sequence stars that are reddened. All of these guys here are way brighter in H alpha than they should be. So remember, R minus H alpha. So brighter is smaller numbers. And we've got minus H alpha. So minus the numbers that are smaller than expected because they're brighter, should end up with a larger number. So these up here are brighter, way brighter in H alpha than expected. So these are the ones that are bright in H alpha. Now they could be bright in H alpha because they're active, they have lots of flares, but the size, the amplitude of these guys are the ones that are bright in H alpha because of flares. These guys are bright in H alpha because they were accreting, so they're young. And the extra bonus is that, look, the reddening vector is this way. So no amount of reddening, there's a lot of reddening uncertainty, but no amount of reddening is ever going to push these guys back to here. So it doesn't matter how poorly I know the reddening for these guys too. Reddening is only going to push them back to here, and that's not going to do anything for making the H alpha go away. So these guys are unambiguously bright in H alpha. All right, and then just for completeness sake, there are some places where you can find Stromgren photometry, specifically because colors don't have this distance dependence, and specifically because of the high mass stars like OBA and to some extent the Fs. Bent Stromgren came up with some specific band passes and combinations of them, which are really, really good for figuring out the effective temperature and our reddening resistance. And so they have these combinations. It's kind of rare to find it, especially for those of us who study the lower mass stars, but you do see it sometimes, especially when people are looking for the high mass stars. And one of my NITARP teams did have this, which is why I have this slide at all. I just leave it in for completeness. All right, now let's link some of these excesses to SEDs, which we haven't yet fully discussed, but we will shortly. This particular guy is from a 2019 NITARP team. It is a young star candidate. This black line here, it's an SED, so this is spectral energy in log against wavelength in log in microns. This black dashed line is to guide the eye. This is where the photosphere would be, assuming that the K-band is on the photosphere, which is not always a good assumption, but it probably is for this star. Clearly, it has an infrared excess. This chartreuse line is a fit to the SED between 2 and 25 microns. So clearly, it has an infrared excess. There is a line here to guide the eye on the Veen side. So that teal line is totally an eyeball line, but it is also where I expect the photosphere to be. Look how high above that extrapolation of that line this band is. This band is the G-band measurement from pan-stars for this object. So what's going on is this is spillover from a huge ultraviolet excess, because G-band is not ultraviolet, it's blue, but the UV excess in the star is so big that it's spilling over into G-band. In order to do a better fit of the Veen side, I need a spectral type so I can get a guess at reddening, so then I can make a model that fits it. I tried for other NITARP teams to use G-band excesses, but it didn't work for other regions. So I think we need a combination of age of the stars and low enough extinction and a good combination of stuff to really effectively use G-band excesses to look for young stars. So your takeaway points from this chapter are that, and remember that colors are differences in magnitudes, which are ratios of fluxes. And they're always bluer minus redder, so that smaller is bluer and larger is redder. So when you make plots of colors and magnitudes, it helps you study the properties of objects you know. And then you can apply those properties to understand the nature of objects you don't know. Because the optical points are largely on the Wien side of the SED, sometimes, if not often, straddling the peak of the SED, you can tie them really effectively to effective temperature. When you find excesses from either the ultraviolet or the IR, you can identify them from the color or color magnitude diagrams or in the SEDs.